In this lecture, we will be working with Kaggle's housing price prediction dataset. It's not a very big dataset, and probably for this problem, it's not a very realistic dataset, but it's a very interesting dataset, at least from teaching and learning perspective. As usual, I have downloaded the data. I have saved the data under this housing Kaggle directory, and I have put this directory under our data directory. As usual, I'm splitting the data before doing anything. And here are first few rows from our train DF. What is our supervised machine learning problem here? We are given features associated with different properties. Each row here represents a property, and we want to predict sale price for each property. So that's our prediction problem. Given features associated with properties, we want to predict sale price. And since our target is continuous, this is a regression problem and not a classification problem. Let's look at the shape of our training data. We have around 1,300 rows and 81 columns. So as I said before, it's not a very big data set. Now let's separate X and Y. We are creating X train, Y train, and X test, Y test here. Okay, now let's carry out some preliminary EDA. I'm calling describe on train DF. What do we see here? First thing I see is this ID column. This is just an identifier column, and we might want to get rid of it. Second thing I see is that this particular column has some missing values. So we will have to deal with missing values when we build our models. Pandas Profiler is a popular tool to get an elaborate EDA. We are not going into the details here, but I quickly want to show you how to use Pandas Profiler. Now, Pandas Profiling is not available in our course environment. So if you want to run this code, you will have to install it on your own in the course environment. I am providing the command here. And here I already have run Pandas Profiling because it takes a while to run it. When you run Pandas Profiler, it gives you a lot of interesting information. First, it gives you this overview, which contains some general statistics. Then, for each feature or each variable in your dataset, it will give some detailed information. Let's look at the overview first. We have 82 features, that is 82 variables, 1,314 observations, that is number of examples. We have some missing data, and the percentage of missing cells is 5.8%. We do not have any duplicate rows, and this is the total size of our data in memory. Now it also gives us this categorization of numeric, categorical, and Boolean columns in this particular case. Now note that Pandas Profiler came up with this categorization automatically, and it's not necessarily correct categorization. We should always take it with a grain of salt. Next, it gives us information on individual features. Let's look at information of this particular feature, lot area. We see that it has 973 distinct values. It doesn't have any missing values. This is the mean value for the feature, this is the minimum 1300, and this is the maximum value for the feature. If we look at this plot, which shows us the distribution of values, we see that most of the values occur in this particular region. And we have some outliers here. What are outliers? Outliers are the points which are very different from the rest of the points, and they can cause trouble in training, etc. So for this particular variable, we have some outliers. We have information about all other variables, and we can also look at interactions between variables, then correlations between variables, missing values, and so on. So there is lots of interesting information here. One point I want to make here is do not blindly trust all the information given to you by automated tools such as Pandas Profiler. For example, if it tells you that certain variable is a categorical variable, how does it actually figure that out? It will look at the Python data type. If it is a string type, then it will say that it's a categorical variable. But we know that that's not always going to be true, right? There could be some variables which are actually ordinal variables, and you want to apply different kind of encoding on these variables. Or there could be some free text columns. If it sees a free text column, it's going to encode it as a categorical variable. But we know that we usually apply different kind of encoding on text columns. So it's always a good idea to look at the data description file and try to make sense of each variable on your own. So for example, in our case, this is our data description file from Kaggle. Now, there is a lot of information here, and I'm not going to go through everything, but I just want to point out that this particular variable, for instance, external quality variable, Pandas Profiler will tell you that it's a categorical variable. But if you look at the values like excellent, good, average, fair, and poor, then it looks like ordinal encoding would be more appropriate in this case. So the point is, do not blindly trust all the information given to you by automated tools. So we have mixed feature types and a bunch of missing values. Now let's identify different feature types and transformations we want to apply on these different feature types. First, I'm getting numeric looking columns. I'm doing that by selecting columns with data type np.number. And these are our numeric looking columns. Now sometimes a column looks like a numeric column, that is, it's encoded with numbers, but it's not necessarily a numeric column. Here is an example. If we look at unique values of MS subclass feature, then these are the unique values. And when we look at the description of this particular feature, it says that this feature identifies the type of dwelling involved in the sale. And here is the explanation for each of these values. So it's not really a numeric feature, right? It's a categorical feature, and it makes more sense to apply one-hot encoding on this feature. Here is another example. This month sold feature is encoded with numbers, but it's not really a numeric feature. It's a categorical feature. Now let's create lists for different feature types. First of all, we would like to get rid of this ID feature, so I'm putting it in this list of drop features. Next, let's create a list for numeric features. I'm taking all numeric looking features here except these month sold and MS subclass features. Now it's possible that some of these features are not actually numeric features, and I miss spotting such features. If you find such features, please let me know. We will be treating these two numeric looking features as categorical features. There are a bunch of ordinal features in this data set. I'm going to categorize these ordinal features into two groups. In the first group, we have ordinal features with the same scale. So all ordinal features from this group have the same ordering of poor, fair, typical, good, and excellent. We will be calling these ordinal features regular. In the other group, we have ordinal features with different scales. We will be calling these ordinal features as ordinal features others. Now let's define these ordinal features and the ordering for them. These are our ordinal features regular, and this is the ordering for these ordinal features. Remember that for these ordinal features, all of them have the same ordering. Now remember that when we create an ordinal encoder, we need to pass ordering for each ordinal column. So that's what we are doing here. This is the ordering for our first ordinal column, this is the ordering for our second ordinal column, and so on. So we will be passing these categories in our ordinal encoder. Our second group has ordinal features on different scales. These are our ordinal features others. And this is ordering for each of these features. Again, we will be using this ordering when we create our ordinal encoder. So far, we have our numeric features, ordinal features regular with the same scale, ordinal features others with different scales, and drop features. Our categorical features are going to be the remaining features. So that's what we are doing here. We are subtracting all these features from X-train columns, and that's going to be our categorical features. Okay, now we have different feature types. We are not really doing it here, but in real life, you would come up with your own features, either by combining some available features or by extracting information from some external sources. A trick question for you. Would price per square foot be a good feature to add in this context? Okay, we are ready to apply feature transformations. Since we have mixed feature types, we will be using scikit-learn's column transformer to apply different transformations on different feature types. Let's create this column transformer. The first transformer from our column transformer is going to be this numeric transformer for numeric features. We create this transformer by creating a pipeline. The first step of the pipeline is simple imputer for imputation, and second one is standard scaler for scaling. The second transformer from our column transformer is this ordinal transformer regular, which is for ordinal features regular. Again, this transformer is created using a pipeline. The first step of the pipeline is simple imputer for imputation, and second step is ordinal encoder. And now when we are creating this ordinal encoder, we are passing the categories we created for ordinal features regular. Our third transformer is this ordinal transformer other, which is for ordinal features others. Again, we are creating this transformer using a pipeline. The first step is a simple imputer for imputation, and second step is ordinal encoder. And now we are passing the categories we created for ordinal features others in this case. Our fourth transformer is this categorical transformer for categorical features. Again, we are creating this transformer using a pipeline. The first step is simple imputer for imputation, and second step is one-hot encoder. And this is our column transformer. I'm calling it preprocessor. We are dropping the features. Then this is our numeric transformer for numeric features, our ordinal transformer reg for ordinal features regular, then our ordinal transformer others for ordinal features others, and finally our categorical transformer for categorical features. Let's examine the preprocessed data. I'm calling fit on our preprocessor, and these are named transformers of our preprocessor. As expected, we have 4 pipelines here. The first one for numeric features, second one for ordinal features regular, third one for ordinal features others, and fourth one for categorical features. And we can see that proper ordering has been passed to these ordinal encoders. Now, if we want to look at our data as a data frame, we need to get the column names. Now, numeric features, ordinal features regular, ordinal features others, they're not going to add new columns. But our one-hot encoded categorical features are going to add new columns. So how can we get names for these newly added columns? Let's try that. Here I'm creating one-hot encoded columns. And how am I doing that? We can do that by accessing this one-hot encoder from pipeline 4 and then calling get feature names on this one-hot encoder. It will give us newly created column names. And that's what I'm doing here. I'm accessing this pipeline 4 from named transformers. I'm accessing one-hot encoder using named steps, and I'm calling get feature names on categorical features. And this is going to give us all newly created columns by one-hot encoder. So now our new columns are going to be numeric columns, that is numeric features plus ordinal features regular plus ordinal features others plus one-hot encoded columns. And this is how our transformed data looks like as a data frame. So initially we have all numeric columns, then ordinal features regular, ordinal features others, and these are our one-hot encoded categorical columns. Okay, now let's look at X-train shape. So that was the shape of our original data. And now let's look at the shape of our encoded data. So we went from 80 features to 263 features. And now that we have our column transformer, we can create a pipeline with preprocessor as the first step and scikit-learn estimator as the second step. And we can conveniently pass this to cross-validate. So that's great. We spent a fair amount of time on pre-processing here, but there is still a lot of room for improvement. For example, right now we are using simple imputer for imputing missing values. In reality, you would be more careful about this. You would go through the columns with missing values more carefully. If a column has many missing values, then probably it's just worth to get rid of that column. Or it's also possible to use more sophisticated ways to impute values. Also in EDA, we noted that there are some outliers in some of the columns, and we didn't really do anything about them. So there is a lot of room for improvement, but for now, this is good enough.